Welcome to Michael Becker. He is talking about data science. It's easy as pie.
Thanks, everybody. So, quick show of hands. How many of you are data scientists? You're going to be really bored. How many of you are data hipsters? You don't like calling yourself a data scientist? All right. And how many of you went to Brandon Rhodes' Pandas talk this morning? Okay, cool. So thanks everybody for coming out to my talk. My name's Michael Becker, and I work in the data science team at Aweber. Aweber's an email marketing company located right outside of Philadelphia. And I'm also the founder of Data Philly, which is a meetup in Philadelphia surrounding data. We have over 1,000 members. So working on the data science team at Aweber, I've introduced several predictive algorithms into our application. And my coworkers think I'm some kind of math superhero, reading scholarly papers by day and fighting crime by night. But the truth is much more sinister. So fortunately for me, I don't have to be a math genius to look like a superhero. I just have to use Python. And while I'll cover some math in this talk, I'll mainly be keeping things high level. So what I'll cover today, I'll start off by defining what is data science. And then I'll teach you the awesome data science process. I'll demonstrate how to create a custom web scraping bot. I'll convert the data that we scrape with the bot to plain text. I'll explore the data using Pandas, Seaborn, and sklearn. And finally, I'll walk you through creating a predictive model using sklearn. So what is data science? Well, there's a lot of disagreement on this subject, but I personally like, and I think a lot of other people on the internet like, this Venn diagram that was created by Drew Conway, which gives a good high-level overview of what skills are involved in data science. So Conway argues that at a minimum you need these three skills to be a good data scientist. So that's hacking skills, math and statistics, and substantive expertise. So in the hacking skills area, he includes things like manipulating text files at the command line and thinking algorithmically. In the math and statistics part, well, I think that's pretty straightforward. And as for the substantive expertise, he includes things like understanding the data that you're actually working with and having domain knowledge and expertise around the type of problems that you're trying to solve. So I'm not sure if it was Hillary Mason who first coined the term awesome, but that's who I learned it from. And awesome is, I would call, a typical data science process followed by many data scientists. So let's break it down. So the first step is pretty straightforward. To do data science, first you need data. Not all the data is easy to access, so be prepared to jump through some hoops to attain your data sets. Okay, so now you have your data. Now what? If you're lucky, your data will be well structured and easily parsable, but in the real world, that's rarely the case. So, and messy data is the norm, not the exception. But don't panic. Scrubbing your data is just another part of the job. So to get the most out of your data set, you need to understand it. And this is where the explore step comes in. This can be as simple as looking at your raw data in a text editor or as advanced as running machine learning algorithms on it. And sometimes you want to predict the future using your data. And this is usually where machine learning comes into the picture. And the goal here is to maximize the predictive power by minimizing the level of error. And a model isn't useful in a vacuum. This is where the interpret step comes in. Often, while interpreting the results of your model, you'll identify areas for improvement, which will allow you to iterate and iteratively improve on your algorithm. And even a bad model can lead to useful insights. So, as I said in this talk, I'm going to walk you through the OSEMN process. Throughout the talk, the example I'm going to be using is a language classification algorithm. And we're going to design one from scratch. And so a language classification algorithm will predict the language of some text. For example, you might give as input the phrase yada, 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 and it might classify that as English. And language classification can be useful on its own. The particular algorithm I'm going to talk about today, I actually use at Aweber for helping us break down our customers by the type of language they use in the emails that they send. And so it can be a useful pre-processing step. For example, in Google Translate, when you type in something to Google Translate or Google Chrome, it's going to automatically detect the language, which can be useful for figuring out which language translation algorithm to use, for example. Or in Google Chrome, it might be useful for identifying that the page you're looking at is not in your native language and suggesting that you translate it. So step one is obtaining the data. And in the case of our language classification model, we need text in a bunch of different languages. Fortunately, Wikipedia has an abundant supply of this kind of data. And there are Wikipedia data sets available online, but that's not much fun. So let's build our own. So to start off, there's this awesome site, the Wikistats files site, which has stats, hourly page view stats for Wikipedia. And so to start off, I grabbed some of these data dumps and aggregated them for several months, and then I compiled a list of the top articles by language. And then I kind of abused the special exports page of Wikipedia to export the pages that I wanted. And this is made trivially scriptable by using the copy as curl command in Chrome. So if you're not familiar with this, it's a really cool command. If you open up the developer tools in Chrome, and you take any request that your browser has made, you can choose copy as curl. And that's going to give you something like this. And then there's this pretty cool library I found. You can get it on PyPy called uncurl. And what that will do is it will convert your curl command to a request library request. So now that we've obtained our data, the second step is to scrub it. And the data that's dumped by the Wikipedia export page is in XML format. So we'll need to pull the text out of this XML. I found another library on GitHub and called Wikipedia Extractor. And it already kind of does this for you. It extracts the text for you. And the tool produces output that sort of looks like XML itself. It has these doc tags at the top and bottom, but if you try to use an XML parser to parse this, it actually is not parsable. So I wrote a regex, a regular expression, to parse out the actual text from this tool, and then what you're left with is just the raw text. All right, so now that we've scrubbed our data, let's explore it some. So I'm going to be using Pandas in the next few slides, so I wanted to give a basic overview of what Pandas is. Pandas is a library with two main data structures, and you can use it for it's really useful for data analysis. So the first data structure is the series, and it's sort of like a Python list, but it has an index. And one way that you can initialize a series is like this, by passing in a dictionary as input. And the first column in the output here is the index, and the second column is the values. So you can access a value by index like this, just using the square brackets. And similarly, you can also access by location, so you can access the first element. It's a zero indexed. By using the ilock method. And a data frame is similar to a series, but it's two-dimensional. And again, it also has an index. And you can sort of think of a data frame as a mix between an Excel spreadsheet and a SQL database. So, but it's Python. And I think it was at least partially inspired by the data frame data structure, which is built into the R statistical programming language. So you can initialize a data frame similar to a series. We can pass in a list of dictionaries. And if you're using Jupyter Notebook, which is what I personally use for data analysis, the data frames will be kind of pretty printed as a nice HTML table like this. So you can access the values in a column, again using square brackets, similar to a series, and that will return everything in the column as a series. And you can access the values in a row using the iloc method, and again it will return a series, but that will give you the entire row. And you can fill in empty values by using the fill-NA method, which will fill in those empty values with, in this case, with zeros. And you can plot the values of the columns using the plot method. And in this case, I'm using a plotting library called Seaborn, which just magically makes your plots look nicer. So, all right, we've covered the basics of Pandas. Now let's explore our Wikipedia data. So to start off, I counted the number of times that each character occurred in every language, and then I grabbed the top 2,000 characters from each. So let's kind of break this down. So first I'm using a counter data structure here, which is part of the collections library in Python. And we're counting the number of times each letter occurs. And then we're taking the top 2,000 from those counts, and we're appending them to this top letters list here. So storing the data as a list of dictionaries like this makes it really easy for us to load it into Pandas. So you literally just pass it to the Pandas data frame here, and again, we fill in the missing values, because some languages have some letters that other languages don't have, so we fill it in the missing values with 0. And then once we have the counts all in a nice data frame like that, and as you can see this, sorry to go back here, but as you can see, this data frame has 10,000 columns. So in this case, each of the columns is a character, and the rows are the languages. And so the first thing I wanted to do was calculate the percentages of the letters, of the letter counts. And so we can do this using the div method, which divides, in this case, all the individual letter counts by the total number of letters for each language. And we can then add these percentages along with back into the data frame with the original counts, and put them in a new data frame using this join method. And in this case, the R suffix argument will name the will add the suffix PERC to the end of all the characters for the percentages that are calculated. And so a join on data frames works similar to a join in SQL. Pandas supports left, right, inner, and outer joins. And for those of you who aren't familiar with what a join is, you can think of it like a Venn diagram. So it's a method for combining data from more than one data frame, and by default, Pandas uses the left join, and that means that the resulting output will contain all the rows from the left, in this case, the original data frame, and it will throw out any rows in the right data frame that don't have matching keys in the left data frame. But in this case, the keys are the same in both our left and our right data frame, so it's effectively the same as any other type of join. And okay, so now we're left with a data frame that has the percentages of letters by language, and it looks a little bit like this. It's kind of cut off since there's 10,000 columns. You can't really see them all. But you can see, I think when I took this screenshot. I was probably using Python 2 because you can see some of the characters don't appear to be printable on the very left-hand side there. These are the percentages of character usage in each language. So the next step is we're actually going to use some unsupervised machine learning techniques to help explore our data. So let's start off by defining what machine learning is. Personally, I like Jake Vanderplas's definition of machine learning. So he says, machine learning is about building programs with tunable parameters that are adjusted automatically so as to improve their behavior by adapting to previously seen data. There's two main types of machine learning, supervised machine learning and unsupervised machine learning. In supervised learning, we have a data set that's consisting of both features and labels, and we're trying to create an algorithm which will predict the label given a set of features. So what's a feature? A feature just might be like a series of numbers, like our percentage counts from the data frame they were just looking at, for example. And language classification is an example of supervised learning. In unsupervised learning, the data has no labels, and we're trying to find patterns in the data. And you can think of the unsupervised learning as a way of sort of discovering labels when all you have is data. All right, so let's combine two unsupervised machine learning techniques to visualize our data. Not sure if you can really read this in the back, but let's break this down a little, what's actually going on here. So first we run this algorithm called KMeans Clustering on our letter percentages. And what KMeans does is it automatically tries to group together the data based on similarity. So what is KMeans exactly? So this is kind of a visualization of a bunch of different clustering algorithms that are built into scikit-learn. And so clustering is an unsupervised learning algorithm that groups together data points that are similar, finding clusters in the data. So as you can see, KMeans, which I've highlighted here on the left, doesn't perform as well as some of the other algorithms at clustering. So for example, dbScan, but KMeans scales a lot better on larger data sets than some of these other clustering algorithms, and it's reasonably quick. So to kind of like show you what exactly KMeans is, I wanted to show you it in action. There's this pretty cool website. I think I might already have it open. Let's see. So this is a pretty cool website. What it does is it allows you to generate some randomly somewhat clustered data. So in this case, it looks like we have roughly 3 clusters here, and it allows you to see. So KMeans is an iterative algorithm, and that'll become clearer when I kind of step through here. But it goes in steps. So right now we're at the very beginning when we haven't initialized anything, and the first thing it does is it randomly chooses start points for the cluster center, so that's what these colored dots are here. And every time the algorithm iterates, what it does is it takes all the points of data, and it figures out which of the cluster centers is closest to that point of data, and it assigns it to that cluster, and then it averages the locations of all the points in each that have assigned themselves to each cluster, and it moves the cluster center to the average value. And eventually, so every step, the cluster center moves closer to what good cluster center would be, and eventually the algorithm converges and the cluster centers stop moving, and that's when it stops iterating. All right. So after we run the KMeans clustering algorithm, kind of clustering together the languages based on the percentage that the characters show up in each language. The next thing we want to run is PCA. So PCA stands for Principal Component Analysis. And in this case, we're going to use PCA to reduce the dimensionality of our data from like 10,000 characters down to 2 dimensions. And the reason for this will become clearer in a few slides. So what Principal Component Analysis is a dimensionality reduction technique that can find the combination of input variables that explain the most variance. And it does this by projecting higher dimensional data into a lower dimensional space. So here's a kind of a nice graphic showing what this means. So you have the white dots here are data that was originally in 2 dimensions, and it's being projected down into a 1-dimensional space, which is what you see in these blue dots on this green line here. And since our data set has over 10,000 features, we can't really easily display this in a graphical way, since we can really only see in 3 dimensions. You can kind of play with that and maybe get 4 or 5 dimensions if you like use different symbols or special colors and things like that. But generally speaking, we can only see in 3 dimensions. So, but what we're gonna do is we're gonna use PCA to convert our data down into 2 dimensions, and that will make it really easy for us to visualize. So this is what it looks like after we run PCA and we plot the results. Since our data only has 2 dimensions, it's pretty easy to plot, and the color for each point corresponds to the cluster that the K-means algorithm assigned to it. And we can see, I assigned 4 clusters. I did this basically experimentally. I tried 3 clusters. It didn't quite look right. I tried 4 clusters. That looked okay. 5 didn't quite look right to me either. So, but there's a pretty clear separation. I mean, you have a big cluster of languages over here. You have another pretty big cluster of languages over here, and there's one, down here, and another one up here. But there's some, there's some clear outliers. And digging into the details revealed that most of these languages use their own unique character sets. So that's kind of why they're outliers out there. And so another way that we can kind of explore this data is by using the pairwise distances function that's built into scikit-learn. And so we can use this to find which languages are most similar. And so the function calculates the distance between each pair of points, and the smaller the distance, the more similar the points are. So, going through our clusters and printing out the distances, we can see that the most similar languages are in our first cluster. So Croatian, Serbo-Croatian, and Bosnian are the most similar, followed by Indonesian and Malay, and Danish and Norwegian, and then English and Scots. And some of these languages are really similar, like the numbers are really small, like the ones on the top there are 0.0038. So they might be useful for benchmarking our classifier later on. So finally, Seaborn has some really awesome graphs built into it, which we can use to visualize the similarity of the languages without reducing the dimensionality using K-means. And here we have a violin plot. And if you're familiar with a box plot, what this is showing is it's showing the middle line here is the median, and the 25th percentile of the data is up here, and then 75th percentile is down here, and then this is the general distribution of the data. And so these plots are going, the more similar the languages, the more similar these plots are going to look, basically. And Seaborn has a ton of other really awesome built-in visualizations that you can use, Pandas, pass in Pandas data frames into them, and they'll give you all these pretty visualizations. So you should definitely check it out. So now that we've finished exploring our data, it's time to build our model. So our model is, again, what's called a supervised model. And so let's start off by defining what is a supervised model. So you start off with some input. In this case, our input is our Wikipedia articles. And this is called the training set. You also have some labels for each piece of your training set. In our case, the labels are the languages of the Wikipedia articles. And you'll note that this is different from KMeans and PCA because in KMeans and PCAs we didn't have labels. And that's the main difference between supervised and unsupervised learning. So next we convert the data to a numerical form, which is sometimes called vectorization. And then we train our machine learning algorithm using our vectorized input and the labels as well. And this is often referred to as fitting the model. And at this point, you have a model that you can pass in a new piece of data into the model, and it will make a prediction about what the expected label is. All right, so let's see how this works in practice. So in the case of our algorithm, you provide some text as input, some Wikipedia article as input, and it will classify the language of that text. And so the first thing that we do is we start off by converting our text to that numerical form, which is called vectorization. And in this case, we're going to use a TF-IDF vectorizer to convert them to numerical form. And what it does is, what a TF-IDF vectorizer does is it first counts all combinations of n character sequences in the data set. These are called n-grams, which is what this parameter here refers to. And then it applies the TF-IDF algorithm. Well, that sounds fancy, but what does that actually mean? So what's this TF-IDF thing? Well, it's pretty simple. It's just the frequency of x in y times the natural log of the total number of documents divided by the number of documents containing x. You get all that? So I don't know about you, but personally I need an example to figure out what the heck that means. So let's walk through a basic example and show exactly what the TF-IDF vectorizer is doing. So first we start off by counting. Again, we're using the counter data structure from the collections library. So let's just keep things simple in our example by counting unigrams, which are single characters. So here we can see that the most frequently used character is space, which I think is at the top here, and followed by the letter O, which was used twice. And this is the TF, or term frequency, part of the TF-IDF formula. And then let's do the same thing with another document. This time it's in German. And the next we calculate the document frequency. So this is the number of documents that contain each character. So we're just taking our character counts and grabbing the keys, which will give us a count of 1 per document in this case. And we can see that some characters are used in only one document, others are used in both. Space, for example, is used in both documents, and there's a bunch of other ones. So this represents the denominator in the IDF, the inverse document frequency calculation. And next, we sprinkle in the rest of the math. So we take the total number of documents, and we divide that by those document frequencies we just calculated. And then we take the natural log of that, and which gives us the IDF portion of our formula. And you'll notice how characters that occurred in both documents are getting an IDF value of 0. So let's put this all together by multiplying our term frequency by our inverse document frequency. And what you get is characters that occur in both documents get a value of 0, so both documents had space. So it's what this is basically telling us, and TF-IDF is nice for this, is that space, since it occurs in every single document in our corpus, is not very important, so it gets a value of 0. And characters which occur more frequently or more unique get a higher value. So O only occurred in our English input, and it occurred twice, so it gets the a higher value there. So going back to our model, again, we're using TF-IDF to do all this work for us. no reason to write this from scratch. In this case, we're actually looking at bigrams and trigrams, so like all combinations of 2 characters and all combinations of 3 characters. And you'll notice that we've also specified that to use the character analyzer. By default, the TF-IDF vectorizer uses a word analyzer, which looks at words separated by spaces as opposed to individual characters. So the next step is this thing called SVC. So that's our supervised learning algorithm, and it's called support vector, or it uses an algorithm called support vector machines, and it takes numerical data as input and into its fit method, and then once it's fitted, the SVC can predict the label of new data points. So let's kind of show you what SVC, or what a support vector machine does. So what a support vector machine does is it tries to find a dividing line between our 2 classes of data that maximizes this distance here between the line itself and the data points in either of the classes. So next we're going to use this thing called a pipeline, which is a pretty slick thing built into scikit-learn. So what the pipeline does is it combines our vectorizer with our SVC classifier. And so a pipeline is a utility class in scikit-learn that you can use to build a multi-step classifier. So the pipeline understands how to connect the output of the vectorizer to the input of the classifier. And all that's left to do at this point is to call the fit method on our model. And but what are these like xtrain and ytrain? Let's kind of dig into that a little bit. So xtrain, again, is the portion of the data that we set aside for training. And xtrain is an array of, it's just a list of text, in this case, Wikipedia articles. And so besides stripping out the wiki markup, we didn't do anything else to prepare our data. The vectorizer handles converting the text to the numerical form required by the SVC algorithm. And ytrain is our labels. So we start off with this thing called, I started off with this thing called Y, which is just the codes, the language codes for the Wikipedias where the articles came from. Unlike xtrain, we actually do need to convert these to numerical form prior to passing them to the fit method. So we can use this thing called a label encoder. A label encoder will take your string labels and convert them to numerical categorical values. And so after that, so scikit-learn, it comes with a bunch of these algorithms built in, and many of them have multiple parameters. This one, as you can see, has a ton of parameters. So if you're new to machine learning, it can be pretty daunting to figure out which algorithm to use and what values to pick for their parameters. But luckily, there are tools built into scikit-learn to help you tune your model so you get the best performance out of it. One of these tools is called Randomized SearchCV. So you give Randomized SearchCV a range of values to try for each parameter. So in this case, we're trying a uniform distribution between 1 and 4 for this C parameter. And for the kernel parameter, we're trying either linear or RBF as input. And then it randomly chooses values for you and tests them. So the other thing that it does for you is it splits your training data into multiple random chunks called folds. It uses a random set of folds for training and another set of folds for testing the trained classifier. So this is called cross-validation. And cross-validation helps ensure that you're accurately measuring the performance of your classifier. So once the random search is complete, you get the highest scoring classifier along with its scores and parameters. And you can easily run this kind of search on multiple algorithms to figure out which one will perform best for your particular data set. But if you're new to machine learning, you might also want to check out this library called Skll, S-K-L-L. It automates a lot of the details, and it has built-in functionality to test multiple algorithms. So once we've tuned the model, it's time to validate that it's accurate. The metrics module in scikit-learn has several utilities for measuring classifier performance. So let's go through a few of my favorites. But for the purpose of testing our model, I've actually left out some of the data from the training. Generally speaking, you don't want to train an algorithm using your full data set because many algorithms can suffer from an issue called overfitting. And overfitting is when a model is very good at making predictions about your training set, but when presented with new data, it performs poorly. So here's a good example of overfitting. The black line here is a nice, as you can see, it's a nice smooth function, and it separates most of the blue dots from the red dots. And the green line you might think is a better fit because it actually separates all the blue dots and the red dots. But it's much more complicated, and it might be that it's just fitting noise in our data, and it might not generalize well to new data. So all the metrics functions that I'm going to show you take two arguments as their input. One is yTrue, which is the correct label for each sample that in our testing set. And the second parameter is ypred, and that's the predicted label for each sample. So accuracy is pretty straightforward. It's pretty much what it sounds like. It's the overall percentage of correct classifications. 96% isn't too bad, but can we do better? Classification report, it builds a nice little text report showing the main classification metrics. And what I mean by the main classification metrics in this case is precision. In this case, it's precision, recall, F1 score, and support. So generally what you need to know about precision, recall, and F-score is, 1 is the best value you can get, 0 is the worst value you can get, and support is just a count of the number of times in our test set that we had these classes. So we had 1,500 examples in our test set of each of these languages. Looking at the classification report, you can see that right away that there is something funny going on. In this case, this is with the Bosnian language. And you might recall from earlier during the explore stage that Bosnian was very similar to a few other languages. So could this be impacting the accuracy of our algorithm? So a good way to find patterns in incorrectly classified data is to use this thing called a confusion matrix. And it looks a little bit like this, but that's kind of ugly. So let's visualize it. So this is a little bit better, but it's kind of, there's a lot going on here, and it's pretty hard to read. So let's have a closer look at some of the more interesting languages here. So how do we interpret this? So you'll notice that each language shows up on both the y-axis and the x-axis. And the y-axis shows the correct label for each training point. And the x-axis shows that predicted label that came out of our classifier. And anywhere where the prediction is correct, a cell on the diagonal will have its counter incremented. And if the prediction is incorrect, a cell off of the diagonal will get incremented. And this is a heat map, so what we want to see is like this dark red all along the diagonal, basically. And we want to see the dark shade of blue in all the other cells. So going along the rows, we can see exactly which languages are being confused for each other. In this case, we can see that BS, HR, SH, and SR are often being confused with each other. And it turns out that these are Bosnian, Croatian, Serbo-Croatian, and Serbian. And I'm not a linguist, but according to the internet, these languages are almost identical. And they all used to be like part of the same language called Serbo-Croatian prior to the Yugoslav wars. Hopefully I'm not offending anybody by that statement. So this gives us some clues as to how we can improve the performance of our classifiers. So since we can safely assume that these are all the same language, why don't we just combine them into one category for training our classifier? So doing this is pretty straightforward. All we have to do is go back to where we created our ytrain, and anywhere where we see the labels for BS, HR, SH, or SR, we replace them with some new label. And then we rerun our random SearchCV and retrain our model. And so after doing this, we're able to easily get over 99% accuracy for some of these languages. And if we wanted to distinguish them from one another, we probably could train some more complex models to kind of distinguish them from one another. But before devoting too much time to doing this, you should ask yourself, is it worth the effort? And it really all comes down to the particular application. Eventually, you're going to hit diminishing returns with some of these algorithms, so it's all about how much time you're willing to devote. Okay, so wrapping things up, I do most of my analysis using this thing called Project Jupyter, which provides this nice little notebook interface, which is where I got all the screenshots for my code examples. And I use Pandas, and that helps make data analysis a lot easier. I like to use this library called Seaborn to help make really pretty visualizations. And for machine learning, I use scikit-learn. And if you're looking for like a more in-depth introduction to machine learning with scikit-learn, I recommend you check out Jake Vanderplas's excellent tutorial. He just gave one recently at PyData in Seattle. And if you're new to machine learning and you just kind of want to jump right in, then you might want to check out the Skull library. So that's all I got. Now you can all go onto LinkedIn and update your, your titles to be data scientist. And with that, any questions? It's a lot to take in, so we got plenty of time.
What's been your favorite thing to classify?
My favorite thing to classify? That's a hard question. So one thing, one kind of fun project of work I had was trying to classify the industry that our customers are in, just based on the type of content that they're sending in their emails. That's kind of a fun and challenging project.
So you used a lot of characters to classify the text as different languages, and I know there are algorithms for basically getting rid of all of the extra characters that didn't really help in distinguishing languages. Does scikit-learn have that sort of functionality built in so easily as the others?
So I have like a machine with a ton of memory, so I don't have to use a lot of these algorithms on a day-to-day basis. But there's some things, feature selection algorithms built into scikit-learn. Again, I haven't really used them too much, but yeah, there are algorithms for that kind of thing in scikit-learn.
Hey, thank you so much for giving a good example of kind of entry into data science. At our last PyLadies meeting, that this seemed to be like the thing that the ladies were most excited about, data science. So I was wondering, I'm going to share your talk with them, and it's recorded, right?
I think so, yeah.
Awesome. So, but is there another kind of entry? They were like, entry points to data science. Do you have any other things I could take back to them to Atlanta?
So yeah, like I kind of mentioned in the previous slide, I think really, well, for me, I have a computer science background, so maybe I'm biased, but I always kind of find the scikit-learn documentation itself to be really helpful. The tutorials, there's the scikit-learn community itself, and a lot of the maintainers of the scikit-learn library have given a lot of tutorials over the years, which are all recorded and available online. Those are really awesome, and they give a good general, I think, introduction to machine learning concepts, along with how to do those things with scikit-learn. Yeah, no problem. All right. Cool. Thanks, everybody.